stage over to him. The case of the dark matter was closed 30 years ago. Astronomers had convincingly shown there were gravitational anomalies in galaxy clusters and spiral galaxies. And particle physicists had answered with a miraculous solution so beautiful that cosmology was forever changed. With just one problem. Nobody has detected dark matter on Earth yet, that we probably should have been able to. These 3 decades of confusion saw amazing advances in detector technology, but one thing remains clear. Life is probably not as simple as we thought 30 years ago. Anthony's going to take us through the maze of the last 85 years of dark matter research and arrive at a current diagnosis of the particle hypothesis for dark matter. Professor Anthony Villano obtained his PhD at the Rensselaer Polytechnic Institute.
That's right.
In the field of particle physics. His initial postdoc work was in nuclear physics, where he took a key role in a project to produce supporting measurements for the neutrinoless double beta decay effect. Any relation to beta on the board?
Maybe.
Since 2010, he has applied his knowledge of particle and nuclear physics to the dark matter direct detection effort. First as a postdoc associate at the University of Minnesota, and now as assistant professor at the University of Colorado. Dr. Villano,
thank you. Thank you. All right. Thank you for that nice introduction. And yeah, I'm going to basically go through 85 years. The first 50 years or so are a little scant, but but I'll go through the 85 years of development and where it's kind of led us. But first, let me see. Yeah, I want to talk about a conversation you might have at a party. So if you meet a physicist at a party and you start talking, you might say, "What do you do?" And if it's me, I might say, "I'm not a great conversationalist. I search for dark matter." And then you might say, "Huh." Okay, so that conversation is kind of a failure. Right? Okay. So why did the conversation fail is what I want to talk about today. So I believe it's in this sentence. I search for dark matter. That's fine up until the place where you get to dark matter. If instead, maybe it looked like this, I search for the elusive Atlantic white whale. I claim to you that conversation would go a lot better. And here's why. It's pretty obvious. I'm looking for some sort of whale. And people normally know what a whale is. The whale probably lives in the Atlantic Ocean, and I'm searching for it to make some sort of natural discovery. And to look for it, I must be using some kind of boat or diving equipment. And bonus points, searching for stuff that's elusive is considered super cool. Okay, so congratulations, you communicated effectively what you're doing, and you can engage further in discussions and learn much more about the Atlantic white whale. But what about dark matter? Okay, so from our little exercise here, my mission is pretty clear. I need to tell you what dark matter is. I need to show you why I think it's important to discover. And I need to explain how I search for it. Then I think if you had this conversation at this cocktail party, you'd be in a position, and both of the people in that conversation would be in a position to learn a lot more from each other. And that would be great. So these are my goals tonight. So let's start here. I need to tell you what dark matter is. Okay. So maybe I should just tell you, because we have to define it like the white whale. But I honestly don't know. So that's a problem to start off with. Okay, so I'm not going to give up though. Let's go to the second question. We'll skip the what is dark matter for the beginning and come back to it. I need to show you why I think dark matter is important. Or why do physicists think they need it? Okay, so here's where we're going to kind of start our journey. And we're going to start 85 years ago with a scientist named Fritz Zwicky. And I found the funniest picture I could of Fritz. in 1933. So Fritz was an astronomer and was observing at that time galaxies that were in clusters. And I have a little picture here of not the Coma cluster, which he was studying, but a different galaxy cluster. And so the important thing you want to know about galaxy clusters is they're gravitationally bound in the same way that, say, the Earth is bound to the sun. However, the bound constituents are entire galaxies. And the orbits can be a little bit kind of crazy sometimes. But that's okay. They're enormous lumps of stuff that have gravitationally bound stuff. So that's all we need to know about that. So Fritz Zwicky was looking at the Coma cluster, which has something like 1,000 galaxies and is something like 300 million light years away. Okay, so what did he see? He noticed something peculiar. So basically what his measurement consisted of at that time was just to try to measure the velocities of all the galaxies that were in that cluster. So that was what he did, and listed all of the galaxies out and their velocities. So that's fine. I actually pulled this table directly from that first publication that he had in 1933. And then applied some sort of, maybe I would say, rampantly irresponsible estimation to it. But that's okay. We can do that as physicists. So basically what he said was, look, I counted about 800 galaxies in this cluster. We now know there are more than 800 galaxies, by the way. But that's okay. That's pretty close. And I know that the mass of a galaxy, well, a galaxy has about 1 billion stars, and a star might weigh as much as our sun. So the mass of each galaxy should be 10 to the 9th times our solar mass. So the mass of the entire galaxy is 800 times that quantity. So 800 times 10 to the 9th times our solar mass. But just because these things are gravitationally bound, we know an interesting thing just from Newtonian gravity and normal physics, is that if I just take a random galaxy in there, the average velocity of those guys should be related to the square root of m in this way. There is some constants in front of here, but basically the square root of m, where m is the total mass of that galaxy. So if you calculate what the square root of 2k, k is just a constant, m is, you get something like 80 kilometers a second. But that's a big problem, because if you saw the masses that I listed on this page, they're not 80. They're a lot higher. Okay? So what that implies basically is you could get this to match up, but what you would have to say is, well, I must have miscalculated what m is, right? It must be much bigger than what I saw in the galaxies. Okay, well, that's an interesting thing. At the time, I can imagine, Professor Zwicky looking at his research and being like, well, I'm pretty sure I counted all the lights in the galaxy. So it's kind of like a counting problem. So it's hard to imagine where that could have gone wrong. But it's definitely, the m has to be larger by something like a factor of 400 in order to make the measurements and the theory consistent. Okay, so let's keep that in mind. And then, something like 50 years later, two things happen. Well, one thing is that there was a very interesting paper by Lee and Weinberg. Weinberg is a Nobel laureate who worked on something called Electroweak Unification. So that's a particle physics topic. Right, and around 1977, there's a very interesting paper that I'm going to come back to in a second. But the other really interesting thing is that Vera Rubin at Wright was another scientist who was continuing her work on measuring how stars are bound in spiral galaxies. How stars move around spiral galaxies. Okay, so here's an example of a spiral galaxy, and this is just a Hubble picture. NGC 1300 is the designation of this guy, and it's obviously moving around clockwise here. So what you can say is that just from normal gravitational physics again, what you can say is that a star that's out on the arms here, right, should be moving at a velocity that's related to the mass that's inside of that. In other words, like a spherical shell of radius r, it should be moving at some velocity that's related to its radius from the center of the galaxy. And the equation that I wrote here is just a simple balance of the gravitational force, which is dependent on r. R is the radius, and m is just the mass, and g is a gravitational constant. And if you set that force equal to the centrifugal force, then you have a good equation. And the centrifugal force involves a velocity, a radial velocity squared. So basically what we're saying here is if you take a string and you put a weight on the end of it and you swing it around your head, the string is balancing the tendency of the weight to go out. It's the same thing here, except the thing that's balancing it is gravity, pulling it in. Okay, so that's pretty easy. Okay, so what did Vera Rubin see? Well, these are the two things that I have on the left side of this slide. The two columns are two separate galaxies. And the top plot is a measurement of the luminosity of the galaxy as a function of radius. So basically, what you do is you count how much light coming from the galaxy, from the center, and then at different steps all the way out, and you get these points. And what you can do with that is, if you believe that all of the mass is in the stars of the galaxy, you can get an estimate for how much mass that galaxy has as a function of r. In other words, as I step out on r, how much mass is there, right? And if you do that, let's look at this equation again. You can sort of apply it to this equation and see what the mass is at a certain r, the mass contained at a certain r. And you can use that to predict, by that equation I just showed, what the velocity should be at that r of a star. And that's what these bottom plots are. If you look at the solid line, this is what the velocity should be as a function of radius of those galaxies, right? But that's just a prediction based on her estimate of the mass of the galaxy. But then, the very interesting thing is, she spent a lot of time measuring the actual velocities by just using, say, the Doppler shift effect and measuring the actual velocities of these stars as you go out. And those are the points on these bottom plots for each of these two galaxies. So what you can see is the answers don't agree, right? If I predict that there is, or if I guess that there's some amount of mass based on the luminosity, I predict those velocities wrong, and the velocity of a star out on the arm is actually a lot higher than what I would predict it to be. Okay, so that's an interesting discrepancy too. We always like to make things in physics, you know, every way that you can estimate the same thing should agree with each other. So we want these to agree. And so how can we fix this discrepancy? Well, it's kind of curious because this is another situation where more mass being in there than we predicted from the light that was measured can actually make those two things agree. So that's just another kind of peculiarity to keep in mind. Okay, so now let's talk about this. I sort of teased you a little bit before that there's a very interesting paper, and then I skipped away from it. But now let's come back to it. So this very interesting paper by Lee and Weinberg. So what they suggested was that this missing mass, both the missing mass that I'm talking about in Zwicky's measurements and Vera Rubin's measurements, was actually, could be left over as particles left over from the Big Bang. Well, that's kind of deep. We'll talk a little bit about that. So this missing mass is often called dark matter. So that's maybe my implicit working definition for dark matter. So when I told you we don't know what dark matter, I wasn't kidding. So this is sort of like now is kind of a name for a problem that we have. And this is a possible solution. Okay. And this matter actually has an interesting property because it was missed in both the Zwicky measurement and the Rubin measurement. It was missed when light was being observed. So what we know is that it doesn't emit light. So that's where the dark part of the dark matter comes. Okay? Okay, so what Weinberg and Lee were saying is that a miracle happened. And I'm not kidding here. This is actually what this is known as. This is known as the WIMP Miracle. And why is it called the WIMP Miracle? Okay, well, first of all, what does WIMP mean? WIMP stands for Weakly Interactive Massive Particle. It's just a particular version of what dark matter could be in terms of particles. And I'm going to talk about what particles are in a second. But the reason why it was called the WIMP Miracle is that because of what Weinberg knew from all of his electroweak theory work, was that some of the particles in that theory that he was working on as a particle physicist interact so weakly that what happens in the beginning of the universe is they get produced in this very hot, dense state that we have in the beginning of the universe, right? And then just 10 nanoseconds after the Big Bang happens, they sort of stop interacting with all of the particles because there's not enough density for them to actually find a particle and interact. It's kind of a strange thing to say, but it's kind of like they're kind of like ghost particles. They go through things. They don't interact very, very strongly. And what this whole theory is saying, and this plot on the right, so on the left here I have a picture of the history, sort of a public plot for the history of the universe. So it starts on the left at the Big Bang, a very bright, dense state. And then after a few nanoseconds, it comes to particle formation. And then eventually, after 14 billion years or so, it kind of cools down to what we have today. So that's a picture of the universe. So what Weinberg is saying is that these dark matter guys are being produced right here, but after they're produced, they're doing not much for the rest of the time. They're just kind of sitting around and making the universe a little denser. Okay, that's interesting. And whoops, this is a plot just showing kind of, it's a technical plot, so I won't go over it too much, but just showing how kind of the dark matter density goes down for a while as a function of time. Time is the top axis here. And then it's sort of does what we call decouples. It stops caring about all the other matter, and then it just stays constant for the rest of the age of the universe. So that was their theory, okay? And so dark matter as particles we have. So what's a particle? Here's a little interlude on particles. Well, I can't tell you exactly what the dark matter particle is because, like I said, I don't know. But I can tell you other particles that you're probably familiar with. One, so there are molecules, and you know that they're made up of atoms, right? So those are two, you can consider different levels of particles. So molecules is kind of like a particle, but it's not fundamental because it's made up of many different things. Then there are atoms, which are more fundamental. They're the building blocks of the molecules, right? Then there's nuclei and electrons, which are more fundamental because they're the building blocks of the atoms. And then when you get down all the way to almost the lowest level, you have something like protons and neutrons, which are the building blocks of the nuclei. So the reason why I'm telling you about this whole telescoping ladder of particles is because I'm going to relate everything we talk about dark matter, all the properties, to the properties of the proton. Because I know what the proton weighs, and that's more familiar to people. Proton, for reference, weighs 1.67 times 10 to the minus 27 kilograms. Okay, so we should probably choose a different unit, and I will later. But so it's very light. And the proton is basically the weight of a hydrogen atom, for reference. So, sure, of course. It's okay.
How did they rule out that it wasn't just a gas or other particles and not a particles?
That's a great question. The answer, maybe I can come back to that later.
Yeah, sorry.
Okay, that's a good question. Yeah. So, yeah, good question. Okay, so the miracle happens, and that's called the WIMP miracle. And all this math that was worked out in order to get this average density that the dark matter would have was done with you just pick a mass of something like 100 times the mass of the proton. Sometimes we call that 100 GeV. GeV is a better unit to measure the proton in terms of mass. It's just a different kind of mass unit because the proton weighs about 1 GeV instead of 1.67 times 10 to the minus 27. Okay, so that's why we do that. And it's related to the proton mass because it's 1. So if we say the dark matter is 100 GeV, then that's 100 times the proton mass. Okay, so here we are on the timeline. We're ending up in the mid-80s, sort of mid to late 80s. And I guess I titled this slide, People Start Believing in Dark Matter. And why I titled it that way is because a particular model in cosmology started becoming very, very popular at that time. It's called LambdaCDM. So what cosmology models are trying to do is map the entire energy content of the universe over time from the Big Bang all the way up until today. So they want to keep track of where all the matter is. And, so some of the matter goes into intergalactic medium, like gas, and some goes into stars, and whatever. So that's like a whole model of cosmology. And you have to put the right abundances in from the beginning in order to get it fit to what we observe today in stars and other observations. So this is a model, and I think it's the first model that kind of went this direction. The CDM in it, lambda, don't worry about that, that's related to gravity, but the CDM I'm going to focus on means cold dark matter, right? So this is kind of like a first model that used dark matter, particulate dark matter, like Weinberg suggested, as a main component in describing the whole evolution of the universe, which is kind of exciting. And people still, this is still an important model today for cosmology. So it's sort of endured over that long period of time. Yeah?
Quick question. Is that lambda dealing with Einstein's correction to his theory of relativity?
Absolutely. Cosmological constant, yeah. Right. So this is a model with the two main ingredients are a cosmological constant in gravity and cold dark matter. And the things that have been very exciting about this model lately are that they're sort of big confirmations with the cosmic microwave background measurements and also Big Bang nucleosynthesis. So I'm not going to go into what those are, but what you can know is that those are experimental data that can match well to this model of cosmology. Okay, and this is what the LambdaCDM. The universe is expanding by the cosmological constant at an accelerating rate, and also there's dark matter there. Okay, so at this point, late 80s, early 90s, I would say this is, by the way, this is my assessment of history. I wasn't involved in all of this. But what I say here is that experimentalists said, okay, good enough for me, we'll start to look for this dark matter. Okay? So, and they said to themselves, if dark matter is a fundamental particle, as Weinberg is telling us that it is, and we've described these particles as constantly around us and everywhere throughout the entire universe. And also, they're sort of very rarely interacting. So what that means is that they're not only flowing through us, as it could be, but they're also flowing through the Earth, and they kind of permeate everything. And that's kind of how it has to be in this model. So the reason why I put this snowy day picture up here is that you can calculate what roughly the density of these little dark matter particles would be. And it's kind of, given that you're assuming that the mass is a certain amount, and we don't actually know that. But if that's true, it's kind of the density of like a snowy day like this. But the big difference is when the dark matter hits the ground, it just goes right through. And I feel like we would like that to be true of snow, but it's not. In some cases. Anyway, so then the question that experimentalists were really asking themselves at this point was, but might it interact? So this dark matter flows through us, right? If it truly doesn't interact at all, we're kind of done here, right? But might it interact a little bit? In other words, can it hit off of our matter in a way that we can actually see it? Well, keep that in mind. Maybe it can. Let me think about that. Okay, so like I said, this is when the particle physicists got in. They said, okay, dark matter is all around us. maybe it can interact with our detectors. So around this time, there are actually 2 examples. I think there were more. An experiment called CDMS, which is called the cryogenic dark matter search. That's actually the experiment that I work on. And an experiment called DAMA are setting up their detectors and just kind of waiting to see if dark matter hits them, and they can tell the difference. And if they could directly detect dark matter, that would be a huge sort of complementary measurement to the gravitational anomalies that I talked about. Okay, so and then in the early aughts or mid, just before 2010, there's a bunch of other evidence that started coming out. One is called this Millennium Simulation, which I'll talk about in a second. It sort of tries to see what would happen if you had a universe filled with dark matter and just let it gravitationally sort of clump together. And then there's another thing called a colliding cluster that happened. That's called a bullet cluster. I'll talk about that too. Okay, so for the Millennium Simulation, people said, well, it's a little hard to do observations in the universe because we only have one universe and we have to look at the sky. So let's try to put this on a computer and then we can do anything we want. So that's what they did. So basically what they've done is just take a lot of particles, which might be dark matter particles, and spread them throughout a virtual sort of simulation grid in the computer, and then just plugged in the gravitational laws that we know are true, Newtonian or Einsteinian gravity, and then watch what happened. How do they sort of coalesce? And the answer they got was kind of interesting. When you start with a cloud of dark matter present in the universe, the evolution of matter in the entire universe for the entire history is dramatically different than if you didn't have that dark matter there. And it kind of forms this kind of spongy looking stuff. So what you're looking at here is just a picture of the simulation, and I have a movie of this, which I hope will work in a second, is a slice of the simulation where the purple lines and the lighter colors are like where the galaxies are concentrated. So if you go out on a super large scale, and again, you can see this tiny sort of scale up here, that's 1 gigaparsec. That's like a 14th of the size of the entire universe. So that's pretty big, right? So on that scale, you look at the galaxies and they look like this spongy kind of web. And that's actually because of dark matter. And the interesting thing, or it's because of the matter that they put in that was uncharged and had all the same properties of Weinberg's dark matter. And the interesting thing is that's actually how our universe is. That's been observed people have observed that with various telescopes and things. That's called large-scale structure. So you can look up any number of publications on that. So let's try to see what this movie looks like. So this movie just basically steps through what this sort of spongy layer looks like for different distance scales. And all but so most of these distance scales are kind of like incomprehensible to us. 500 megaparsecs. A parsec is basically 3 light years. 250 megaparsecs, that's huge. Okay, now we're getting somewhere. 125 megaparsecs. But these bright spots in the middle here, what they are is that's where we live. That's our matter and our galaxy and all the light that's in the galaxy. And we're on these stringy things that are strung out throughout the entire galaxy. And that's kind of how the large-scale structure of our galaxy works. And it's... What's that? Yeah, that's what you call them filaments. Yeah.
Is dark matter in the filaments as well as?
Yeah, right. The dark matter is actually responsible for making the filaments collapse there. So that's, let's put it this way, you're going to be going a long distance before you find a gas station if you find yourself in between one of those filaments. That's where there's truly nothing.
Can you run that again?
I think I can. Is it running? Yeah. Kind of slow.
So what is the scale of the local group, do you know?
The scale of the local group is like a megaparsec maybe, I think, or so. So this is truly large-scale structure.
So if what the dark matter with gravitationally interact, shouldn't we observe dark matter solar system, dark matter planets, should we be able to see that in our observations of other solar systems?
That's a good question. I mean, so it's possible that there are, in these filaments somewhere, there are regions that are made mostly of only dark matter. But what kind of tends to happen is that the dark matter pulls in the other matter that's in the universe to begin with, like the gases, and just creates star-forming regions. So that's what all these bright spots are. They're regions where the other gas has been pulled in by that gravitational collapse and has formed stars.
Does that assume WIMPs?
What's that?
Does that assume WIMPs?
It actually doesn't assume exactly WIMPs. It assumes some kind of dark matter that interacts gravitationally. Okay, so here's another piece of evidence that's kind of like interesting. It's called the bullet cluster, and that was observed first in 2006. And it's really interesting because I think it's one of the first, maybe, I'm not totally sure about that, but it's the first, it's the most important and earliest example I know of that really uses gravitational lensing in an interesting way. So what happened here was that there were two galaxy clusters, like those things that Zwicky was studying, and they were coming together, and they actually collided a long time ago, probably. And what was left was basically two things. One, this is what it looks like in the visible light, right? And I'll tell you what these contours are in a second. And this is what it looks like in the X-ray light. So we talked a little bit, this is kind of coming back to a question I had about the gas. So yes, it's true that it's known that there's much more gas in between the stars of these galaxies than actually the mass of the stars themselves. So how you analyze this here is that they pass through each other, and you can see that the gas kind of rammed up into, from each of the galaxies, kind of rammed together, and there's actually like what's called a bow shock from this increase in pressure. And then there's hot regions made by this ram pressure of the gas that emit X-rays. So that's what that is in the middle. But the interesting thing from the bullet cluster is the following thing, that these lobes around here, these contours anyway, are tracing out where gravity tells us most of the mass is. Okay? And that comes from pure gravitational lensing. What you do is you look at the stars in the background behind the cluster, and the light actually bends around any mass, and you can create contours for where the mass is. So given the fact that we know that the gas in these clusters is definitely more heavy, it's kind of confusing that these lobes are on the outside. You would think that most of the mass would be in the inside, and there would just be one lobe and then some small things. So what it means is that the mass retained in the clusters is much higher than what's in the gas. And we can't account for that by what's in the stars. So that's often touted also as evidence of some missing mass, gravitationally seen missing mass. Okay. So, yes. Yes, absolutely. Yeah, and that's kind of the point. Yeah. So there are a lot of big uncertainties on these measurements, right? But also the discrepancies are just so large, right? Okay, so, but wait. Couldn't Einstein just be wrong? In other words, what I'm saying, couldn't gravity just be wrong and then we're doing something wrong? Because I remember the first two examples I gave you kind of depended sensitively on using Newtonian gravity to figure out how fast the disk was rotating or how fast the galaxy should be going. I guess the answer is technically, yeah. The one column, one way you could go is say, well, there might not be dark matter. All we need to do is modify gravity. There's actually a theory for that. It's called MOND, modification on Newtonian dynamics. And actually, it's shown in the 1980s. Actually, yeah, you can get the rotation curves pretty well matched. In other words, the Vera-Rubin discrepancy kind of can go away if you're allowed to modify the laws of gravity on large distance scale. So you wouldn't need dark matter in that model. But On the other hand, on the other column where you believe in gravity, exactly how it is, Newtonian gravity with the Einsteinian completion, general relativity. So there are so many things that also predicts exactly correctly, like bending of light by the sun, or gravitational waves, a new thing. And this picture, when you believe in that kind of gravity, you kind of need some kind of dark matter in order to be consistent with the cosmological measurements and the other gravitational measurements of the universe. Okay, so I'm not sure about the status of how. So modified gravity also has a difficult time, say, fitting in well with the cosmology picture put out by a LambdaCDM model, right? So I'm not sure that I'm going to say that it's definitely not modified gravity at this point, but I'm going to ignore it for the rest of the talk because, because I'm trying to find dark matter in the lab, and if it's that one, then I'm just out of luck. So let's be, for me, that's optimistic. So detecting dark matter only explores this kind of scenario. So if you're saying, I'm looking for dark matter, particle dark matter, you're kind of believing gravity, and the Mon stuff is just a scary thought in your head. Okay, so pause. What have I shown you so far? So I think I tried to show you why do physicists think they need dark matter. So one, gravitational observations, Zwicky and Rubin. They seem to be inconsistent. If you put extra mass there, they might work out. Two, there could be particles produced in the early universe that interact very rarely. This was the Weinberg suggestion, the WIMP Miracle, and he has reasons for suggesting that aside from dark matter. It's beautiful from a particle physics perspective as well, just the theoretical perspective. Three, modeling the universe is easier to do accurately, and I'm talking about large-scale structure and LambdaCDM, with some sort of non-interacting mass floating around. Okay? And the bullet cluster seems to still have most of its mass in the lobes. And if that was, I can't really reconcile that with the gravity, with assuming that we have the same kind of gravity model we have with gravitational lensing. I can't really reconcile that with, it means that there's some kind of something there. Okay, so that's why physicists think they need dark matter. Almost all this evidence is gravitational in nature, kind of, except for the sort of theory thing that's, we like this particle model. Okay, so we better get serious now. It's been like 71 to 75 years. I'm sort of marching along this timeline. So this is like 2009 or so, or so. So it's kind of clear that dark matter is going to be hard to find, though, because if it weren't, we would be aware of it. You would be standing here and you'd say, "Oh, feel that WIMP wind today?" Okay. So, and it's fast too, by the way. So it would knock you over. So now I'm going to address how I search for dark matter. So let's re-examine a little bit about how dark matter might interact. Before I said on the galaxy cluster size, like I said, it's not interacting. That's kind of like on average, right? Could it be possible that it interacts a little bit? If all this dark matter is streaming through our detectors and things, or our just solid matter, might it sometimes knock into a nucleus and knock it away? The answer is I hope so. Okay, so elastic scattering on nuclei, a dark matter particle can come into a solid detector and just knock a nucleus there, and it leaves a signature there. Sometimes there's heat left, sometimes there's liberated charge like ionization, and sometimes there's light. And we could detect those things, right? So that's where this is what I'm in the business of doing, detecting. So how does this measurement work? I want to give you a sense of like what I do on a day-to-day basis in order to do this. So remember, I have this detector sitting there, and like when any particle comes in and makes some liberation of heat, charge, or light, I can measure the energy that was deposited into the detector for that one event. So that's what I do. I sit there with an axis like this, and then I wait. And it looks like this. And I keep waiting. Okay? And then eventually, after a really, really, really long time, this thing will come and make kind of like a shape in a spectrum. So these are just, each event comes in, and all I do is measure its energy and put a little tick on this axis of its energy. This is energy in keV, right? And if I wait a really long time, it's going to make one of these shapes. Well, the good news is I know enough about just elastic scattering. You don't have to know about dark matter too much to know what a dark matter signal would look like eventually. So it depends on the mass. Again, these on the right side here, this is what that shape will eventually look like depending on the different masses of the dark matter particle. So if it weighs 50 times the mass of the proton, it looks like this dark brown line. And it goes all the way out to 100 keV. If it's a little lighter, it goes lower in energy, but gets a little higher. So these different curves are what this will eventually look like. But you have to be patient. You have to wait there a long time. Okay? So the shape of the signal kind of tells us the mass of the dark matter. So I get this thing, I match it up with what this thing is, I say, hey, I discovered dark matter and it has this mass. Great. One big problem. What about something called backgrounds? Those events I showed you are coming in, I tried to stress that they're coming in very slowly. Because of the dark matter is very rarely interacting or shy to interact. There's a lot of stuff we have in life that are not shy about interacting. There are gammas coming off of the potassium atoms in the wall. There are all kinds of different particles that could come into my detector. So if I ran this same experiment on the surface of the Earth and just put my detector there, this is more like what it would look like. Where the red are unwanted events, and the blue are my dark matter signal. Okay, I think you can see this is a problem, right? So I don't have this in my data when it's coming in. I don't get to color them blue and red. I don't know the difference. I can only tell by shape, by the shape of this final spectrum. But the background is completely swamping it. What's that?
You have a lot of noise.
You have a lot of noise. That's right. Exactly. Too much noise. And this is a simulation done with 10 times the background of the signal, and it would probably be even worse than that on the surface of the Earth. Okay, big problem. We can't see the shape of this signal. There's nothing I can do. It's just going to look at like the shape of whatever the background is. So what do we do? Like I said, this is a terrible problem. So first of all, where does this background come from? I kind of said it a little bit, but one thing is radiation in the walls and things like that. You can't get rid of that. But a big problem is the rate of background on the surface of the Earth comes from cosmic rays coming in from outer space, and there are protons that come in and create showers. I tried to draw it here on this little slice of Earth. So cosmic ray comes in and then just makes a huge shower of particles that come down, and they can interact with my detector. And dark matter detectors also respond to these cosmic rays, so I can't build a detector that can definitely get rid of them. Okay, so in order to fix this, experiments had to go underground. This is kind of an interesting, this is actually the part that I would probably talk to you about at the cocktail party if I were trying to engage you, because this is the part that's kind of fun. All of the experiments that I go to when they're eventually running, I have to go deep down into these mines to see the detector. And the reason for that is because it shields out a lot of the backgrounds. So here's what you might expect from an underground experiment where we've shielded out some of the background. So you see, we still have the background in there, and say the background here I'm simulating just 33% of the signal. All right? So we still have the red events coming, but the blue events are clear, and they're coming through, and I can kind of tell they're piling up over here, and there's not so many of them over here. So if I wait on that, like I normally would, yeah, we're good to go with this. The shape, I can still see the shape of the signal. It peeks out from under the background, and we're good. So that's why the dark matter experiments are typically underground. Okay.
What in your detector, what are you, what is recoiling? What element is recoiling?
It depends on what the detector is made out of. The detectors that I am mostly using are germanium or silicon. But there are detectors ranging a lot of different materials. Xenon, a lot of different things. I'll talk a little bit about that.
If the interaction is light, when would you
Oh, that's a good question. So the light that I'm talking about there is scintillation light, and it only really happens when there's a solid sort of crystalline block of material, and that turns out to be pretty rare in the universe. Okay, so let's back up to 2009. So people did this, and CDMS was one of the people that did this, the cryogenic dark matter search, the experiment that I worked for. So in 2009, they published what's called an exclusion limit. Basically, it's this like solid line on this plot. So what this says is, this is on the x-axis here is a WIMP mass, and on the y-axis is kind of like a probability to be detected. And what we say is, based on the number of events we saw, we know that the elusiveness kind of like of the dark matter interactions are at least this much, because we didn't see any obvious dark matter, so we can exclude that it had a certain amount of probability to interact. And you can actually do this as like a function of mass, right? You can assume, because remember, we don't know what the mass of the dark matter particle is. It was just kind of guessed by Weinberg at the beginning. So we can assume a mass of 1,000 times the proton mass, or 100 times the proton mass, or 1 or 10 times the proton mass, and we can get a different sort of exclusion limit based on that. And that all comes from the fact that the shape of the spectrum changes, like I showed you in the previous example. Okay, so around this time, so you can say in 2009, all of these lines are actually other experiments that have also produced these limits from doing the same kind of experiment, but maybe with different kinds of detectors. And this big swath of green and gray are where theory, a particular kind of theory, would have expected us to start seeing dark matter signal in this kind of plane. So the limits are kind of pushing into the theory and excluding more and more of it. So what it means is that this region of the theory is kind of open, but this is excluded because the limits kind of exclude it. So what you can say at this point is that while we're cutting pretty heavily into this theory, we still haven't seen dark matter. Okay, so at this time, the US dark matter community said, basically, we decided we should both try to access lower mass dark matter WIMPs when we're trying to make these measurements, and also try to figure out if dark matter has, at the high mass region, if dark matter can have a lower probability. In other words, try to march this down. Okay, so that's kind of like a schism in the dark matter community that says some people are going to search for low mass dark matter and some people are going to search for high mass dark matter. So boom, that's that schism around the CDMS 2009 result. And some people are going to search for high mass and low mass. And the reason why we did that is because the technologies to search for these different mass ranges of dark matter, since we don't know what the mass is, are kind of get very different when you want to get very sensitive to that. Okay, so I'll show you what this boils down to in the US. There are two experiments that there are many experiments to directly detect dark matter, but here's the two that I'm going to choose because they're US-based experiments, and also they sort of very clearly delineate the low mass region and the high mass region of dark matter searching. So one is called super CDMS, the other is called LUX. And the target material for super CDMS is either germanium or silicon, and LUX, the target material is liquid xenon. Okay, so what does LUX do? Well, basically, they take a vat and they put a bunch of liquid xenon into that vat and wait for dark matter to interact in there. It's set up in a very special way so that they can not only measure the light that comes out directly from that dark matter interacting, but they can also measure electrons as they drift up here with their photomultiplier tubes. These are, oops,
Mines,
that's true.
Underneath the surface. How can you tell the difference, other than the noise, how can you tell the difference whether you detected a WIMP or a neutrino?
That's a great question, and the answer is we can't. So you sort of, you've exposed me, but that's okay. So the answer is we know enough about neutrinos to know exactly when we'll be able to start detecting them. So if we detect more dark matter than we would the neutrinos, we can say, hey, there's something extra there.
Will the neutrino leave some kind of signature that you can identify?
If you find a way to disambiguate a neutrino signal from a dark matter signal, please call me. So no, yeah, so that's a great question. Neutrinos will absolutely interact with nuclei and will absolutely leave a signal, and it'll pretty much be pretty ambiguous for us. But we have thoughts on it, but they're not well formed. Oh yeah, that's right. And that basically has to be true. They're sort of gravitationally bound, or they are the galaxy more or less. Our matter is sort of only like 4%. So yes, and they're just flying around the galaxy. That's right. Yeah, so they're not stopped. If we were stopped with respect to the dark matter and they were just all sitting there really like that snowy day, we would also have no hope. Yeah.
What if the size of the dark matter particle, is going to sound weird, but is the same size as the Earth and it's taking the same space, and we couldn't see it move?
That's interesting. It seems like so two things I'll say. People do look for sort of planet-sized dark matter, because that was a possibility up to some years ago, because usually gravitational lensing can rule that out, because you can look for little planet-sized things. So they look for that. And the other thing is that it would be an amazing coincidence that it was going exactly the same velocity, and so it could pass through, but I would think that it wouldn't be for long.
Okay.
Yeah.
Yeah, so you mentioned that you need crystals to dark matter. I do work with like Villano and stuff, and I know that they're all massive, gigantic crystals of just neutrons that are in like stars. Would you be able to measure the energy? Is there a system, or is there just always too many?
So that's a great idea. You need to think of a different way to do it than the way we do with our detectors, because what we have is our detectors the light sensing detectors, for example, have to be clear crystals, right? So a neutron star is not good because I guarantee you dark matter is interacting in there, but the light is never going to get out in order for us to see it. But based on the fact that the dark matter is interacting in there, there might be some other thing like they heat up a little faster, and if you can think of a clever way to find that out, that would be great too. That'd be great. It's kind of like you would call that indirect detection, I suppose. So I'll just continue. Oh, sorry, yeah.
The problem I have is that all of your math and all that is assuming 3 dimensions. It's like if there's a dimension that we can't perceive,
That's true.
that's interacting with gravity.
I think that's...
It might look the same, but I don't know how you do that.
I think that's possible. So I don't know what to say about assuming 3 dimensions, except that you're right, that we do assume that. And if there are more dimensions, yeah, I'm open to hearing about it. We'll have to rewrite this. Okay, so I was talking about Lux and LZ. LZ is the next, is the predecessor, or is the successor of Lux. So they can detect a piece of light and also, or a flash of light, and also the electrons that are drifting. And that gives them a great way to tell if this interaction hit a nucleus or something else. And if it hit a nucleus, that's a great candidate for a dark matter. So they have a way to tell if a dark matter hit, even though the WIMPs are very shy. And the thing about this technology that makes it a high mass search is that you could just keep making these bigger and bigger and bigger, and they scale very well. So eventually the LZ experiment will be like the size of this room or something, or anyway. So they keep scaling up. Okay. So a trick for a low mass search. So let's look at the energy spectrum that we had. So we got to get a little tricky, and this is what CDMS does to look for very low mass WIMPs. So notice that I was showing you what happens when a background is included in this. This is only the signal spectra that you would see. But if you go to very, very light WIMPs, you see that the signal spectra goes to only a lower energy. It's bounded below, but it also kind of goes up. So this tan line, or whatever that is the lowest WIMP mass that we have here for this guessed spectrum. Okay, that's kind of interesting. So what if I did my experiment again, except I tuned the signal event. Now I'm using the same rate of background that I used originally. Remember when we said that that background was way too much, right? Except I tuned the signal, so I said it's going to be a really low mass WIMP, so it's going to not come out that far. So let's see what happens here. So you see the background coming in real fast, the red, right? And it's all flat out here. But there is signal, and it's not really going so high. And it's kind of sticking up above the background here. Well, that's interesting, because what that says to me is that, okay, if it's sticking above the background, then I can see it there if I actually do this experiment. So that means that even with a really high background, if your detector is very, very sensitive and you can measure these very low energy deposits, now realize this is almost zero energy on this scale, right? But if you can measure those guys, you can still measure dark matter. So that's interesting. We're good to go in a kind of separate way. I said first, you might have to go underground to do it, to get rid of this background. But you could also really get a good energy resolution down there. That's another way. For light dark matter only. Okay, so that's what Super CDMS does. So we have these germanium detectors, and they're sort of, we put a voltage across them, and we have something called a TES array on the top. And I sort of made a larger version of this. So this is what the whole detector looks like in real life. This is a cartoon version, and this is like a larger version of what these TESs are. The TES stands for Transition Edge Sensor, and we're measuring phonons, so like lattice vibrations in these things. So like, remember I said originally that when something interacts in a detector, it can produce charge, light, or heat? Well, this is the heat part, right? And it turns out that these are sensitive to extremely low energy deposits. Okay, so can we really discover something? So one experiment cannot rule them all. At this point, after the 2009 schism, we have to look in the low mass range and we have to look in the high mass range. So within the next 10 years, we'll expand our search over 2 orders of magnitude in the probability of interaction, but also in like 6 orders of magnitude of mass. Because there are experiments coming online that are searching for high mass, for sort of intermediate mass WIMPs around 1 GeV, like the mass of the proton, and also for really low mass WIMPs that are like more like the mass of an electron. So that's a huge range that we're now kind of being sensitive to, and it's all because and I like to hide this fact, kind of because we don't know what we're doing. Well, not because we don't know what we're doing, just because we don't know what the mass of the dark matter is, and we have no great ideas about that so far in terms of particles. What's that?
Why can't we calculate the mass of it if we know that maybe I missed that one?
No, so the only constraint we have from observation from these LambdaCDM models and the gravitational is that in this box, right, I have a certain amount of total mass, right? Now what I don't know is if one particle weighs, 1 GeV and I have 1,000 of them, or if I have less of them and, you see what I mean? So that snow picture that I showed you was actually assuming a certain mass. If I tick the mass down a little bit, then that snow would get a lot more dense.
What if you just say what the total amount of dark matter mass is, but not individual particles?
That's right. And our detectors only measure individual particles. Okay, so, and if we can find them over these next 10 years, it's going to be very important to do really precise measurement with these detectors to understand a lot of different properties of them, like exactly what their mass is, if they have spin like electrons do and protons do, or what their halo distribution, so like what you were saying, exactly the velocities that they're flying through us at, because we don't quite know that either. We have some good estimates. Okay, so that completes how far we've come. There's a bunch of stuff in here. 2018, we're in exciting times, although I would argue that it's been pretty confusing. Or I haven't been present over all these times, but it seems pretty confusing. But maybe our conversation can now go like this. So what do? I search for dark matter. And then someone's exciting, and we can learn more about that going forward. Okay, thanks. Yeah.
So, the question was asked earlier about neutrinos being able to differentiate. How do we know that these aren't neutrinos?
How do we know that? That's a great question. And it's actually known that neutrinos have mass. They have a very light mass. So remember I said in the LambdaCDM model, I kind of ignored the thing. I focused on the fact that CDM meant dark matter, but I ignored the fact that it said cold. Okay? That's actually part of this question because neutrinos are so light that they're always kind of relativistic, right? And that actually won't work for the large-scale structure simulation. They have to be heavy enough so that they're non-relativistic from the beginning of the universe, of the structure formation. Yeah?
Last August, when the neutron-star collision happened,
I don't think. Because dark energy well, okay, they are correlated if you, let me say this thing. So if you look at just the gravitational evidence that I started off with, like the Zwicky and Rubin work, then you don't have to talk about dark energy at all. If you start looking at the cosmological model and how dark matter fits into there, then you might have to start talking about dark energy, because dark energy is, after all, what the cosmological constant is, right? So if you change the cosmological constant, it might be true that in the LambdaCDM model, you also have to change how much dark matter is in there. And that's the way that they play off each other. Yeah. Oh, sorry. You had a question for a second.
How is this fitting in with the standard model?
These are all great questions. So dark matter is not in the standard model. So it doesn't fit in with the standard model. This would be an extension to the standard model.
Are there any theories on dark matter's interaction?
Yes. Yeah. Are there any theories on dark matter's interaction with itself? And so there are a lot of theories. Actually, there's a lot of debate. So one thing that I really glossed over, because we don't have a lot of time, is that when you have a galaxy, and I argued that most of the matter is actually dark matter, right? So these galaxies are a tiny part luminous, and actually the halo, dark matter halo that you can't see is enormous, right? And what people argue about, especially astrophysicists, which I don't get involved in those arguments too much, is that what the sort of velocity distribution of that dark matter is within the galaxy. And that really depends on whether it can interact with itself or not. So there's a huge, debate about, when you get toward the center of the galaxy, there's huge dark matter densities, and is it dense enough to actually be interacting with itself there? And the answer is open. We don't know. Yeah.
In particle physics, they just started finding the God particle that relates to
Higgs boson, yeah.
the Higgs boson.
Right.
Are there any theories that relate to other possible aspects that would have a gravitation?
So all of the particles gravitate, so they have a gravitational sort of component.
There's a Higgs boson which creates all the gravity we know, but is there any other theories in particle physics that would suggest any other type of thing?
So I think this is the best motivated other particle outside of theory. And also the Higgs mostly generates mass. It's less related to gravity than it is to mass of other particles. Although it does interact gravitationally. Yep.
Do our space probes provide any kind of Farah-Rubin-like constraints on how much dark matter mass is in our solar system and its distribution?
That's a great question. There are a number of space probes that might. I wish I could give you a more concrete answer. So there's a space probe that's called Fermi, and it's a gamma measuring probe. It's not observing invisible light. But one of the big analyses that group has done is they pointed that thing at the center of the galaxy and tried to look at different kinds of gammas coming from the center of the galaxy. And they saw some signal, and some people think that that is actually related to dark matter annihilation from the center of the galaxy. So in that sense, yeah, space probe might constrain how much dark matter we do have in our own galaxy. I don't know about the velocity, the measurements of the velocity of the spiral arms. I'm not aware of any other space probes that constrain that.
What I was thinking of more was just the trajectories. I mean, our tracking of the trajectories has been a strong confirmation of general relativity. Wouldn't that be sensitive enough to pick up gravitational effects such as local concentrations of dark matter?
In principle, it would be. I think the problem with our own galaxy is that it's hard to observe the whole. So when you're doing a Vera Rubin kind of analysis, it's good to see the galaxy from a great distance. So you can see. I think you're right that there are space probes that can make very accurate determinations of the paths of certain stars, but you can't see how they relate to the rest of the galaxy as well. Yep.
Sorry to bother you one more time,
Oops.
but it sounds to me almost like we're looking at another fundamental particle here, that we have like quarks and leptons and bosons in this nature. So if I were, from what I gather of your talk, you're looking at dark matter as something of a new particle that would be maybe somewhat equivalent to the Higgs?
It's definitely a new particle, and everything you said is right, except somewhat equivalent to the Higgs. It's sort of separate from the Higgs. Yeah, you had a question.
So in some of the books, I've read that there are probably two types of dark matter.
Oh.
The WIMP, and then one, I think that one is macho.
Huh.
Do you ever deal with that, or?
So that's a great question. Machos are basically this planet-sized dark matter that I was talking about before, and they've kind of fallen out of favor because of gravitational lensing measurements, say, kind of similar to what was done in the bullet cluster, say, well, we looked out for machos, and we haven't really found ones that are large enough to account for all the dark matter. So people sort of are feeling now that maybe machos aren't the answer. That's why WIMPs are better favored. Good question. What's that?
There's not mucho macho.
There's not mucho machos, no. Yeah, I don't know where all these acronyms came from. Yeah.
What about axions?
Axions, great question. So that is not a WIMP. It is a possible dark matter candidate, and they're super low in mass. Like, let's see, much less than a billionth of the mass of a proton. So people are looking for those. It's not my area of expertise. Yeah. Go.
Is it possible that there is no interaction with these particles?
That's a great question. That's an excellent question. I think it's not impossible. However, we would struggle to find where they fit into particle physics if there's really just no interaction.
Well, what if it was like, we was talking about, if there's more than 3 dimensions, and what if, we fill in back in our 3 dimensions, the gravitational particle, but we couldn't use the active particle.
So something like that might be true. We're not exploring those models because they're too complicated. But one model that's sort of similar to what you're saying is sort of, they call these Kaluza-Klein modes of gravity. and they are extra-dimensional manifestations of gravitational particles. And people don't know if they exist. They might be the dark matter, but we need some great ideas to figure out how to detect them if they are. I guess I didn't, well, okay. So let me put it this way. I think they cannot interact. And normally we call that a hidden sector in particle physics. But if they're, I guess the simplest way to say it is they don't have to interact. You're right. That would be called a hidden sector, and there's nothing we can do about it then. Yeah.
So one of the original charts you had showed essentially like we believe there's dark mass because there's a departure from expected velocity of gravity. Almost straight from physics, if you have a point source of gravity, you're going to have an increasingly slow orbit as we go away from that source.
Okay.
Right? And in effect, a galaxy or any cluster of mass operates in that way. Like if we have a galactic source, then yes, there's stars everywhere, but the mass is effectively acting as though it's from the center.
It's acting, so I guess I would say...
velocity is the center of mass. We expected velocity to come from that center of mass, and that's why we expect the velocities to drop as they go outward, as the initial expected chart seems to show.
I think so. The way I would say that is that the velocity of a particle at some place on a galaxy depends on the mass enclosed lower than that r only.
Okay. I'm sorry, what was that?
So, in other words, if you're in a... So galaxies are tricky just because they have mass going all the way out. Right. So the orbit of something that's in one radius doesn't depend on the stuff that's at a higher radius. It only depends on the stuff that's at a lower radius. And in particular, the total mass of that stuff at a lower radius.
Treating it as a continuous body.
Kind of.
But even so, the bottom line though is that, and also it's like when you're in beginning physics, they always had horrible with the aspects of neglecting air resistance is always a complication.
Right.
So in some galaxies you've got a bar structure in the center too. So putting all that aside, just keeping it simple for the moment, we have this common idea that, okay, so for any given particle, there's sort of the center of mass phenomenon with the provision that it goes by the mass that's to that radius or less. And so therefore, of course, as you get the particles, you still expect that drop because the farther out you go.
Absolutely.
So still, you have this expected curve where it drops, in some...
That's true.
In some...
Yeah, so if I...
curve. And the actual result that she saw, the researcher saw, was, roughly, graphically speaking, is almost a flat line.
Right.
Okay.
So
my question, now that we understand, so it's that lower chart, isn't it?
Yep.
The expected curve, the calculated curve, the hypothetical curve is that lower solid line, right?
Yeah, that's right.
There you go, okay. And the actual curve that we got is that dotted line. Like
that's right. Yeah, that's right.
Okay. So the question is this was supposed to be the basis of, we've got too much mass. But then, more or less, shouldn't we still have the same curve shape, but just with a higher amplitude? Why does it change the shape of the curve?
So you're right. I think what you're arguing is that no matter what, we have a clump of dark matter there. So eventually it's got to fall off. Even in this case where we say that there is dark matter.
Clump or no clump? Even if it's a cloud that's evenly distributed, that still acts like the bright mass that we can see. And that chart, that solid line, is where we would expect for a solid material. She was looking at galaxies before we knew about dark matter, saying, okay, according to our understanding of physics and so forth, this light mass, the stuff we can really see, okay, should give us that lower curve, right?
Yeah, that's right.
Okay, so now with regard to the dark mass, which we really don't know a whole lot about, whether it's in a solid or like in a clump, or whether it's in a cloud like the actual stuff we can see, same difference. We should still be getting a curve shape more like that lower one, just higher or lower if there's more mass. Why does it have that different curve shape? Why is it flat lining?
Yeah, so I think I agree with everything you said except for the just higher or lower. So what would happen is if you measured this curve, the problem is that she measured this curve based on individual measurements of stars, right? And eventually you stop having stars. to do the measurement. So this actually should extend way out here and it would go down. And the problem is that the dark matter halo of these galaxies is just so huge compared to the visible matter halo. We're looking at a different section.
It's almost like a game, like if I just graphed two parabolas. One of them we're looking close up, zoomed in, so we see the bowl shape.
Yeah.
One of them is we're so far zoomed out, all you see is a vertical line because that's really what the curve looks like.
Excellent analogy, and I think that's exactly right. So if you could actually measure this out, I think it would eventually go down. Problem is that look at this luminosity profile as it goes down. There just aren't any stars out there to do the measurement. Yeah.
So I know we talked about solar cluster and how the X-ray emissions and the dark matter, and the gravitational lenses measurements down that track. Would we be able to see something similar in like galaxies? I know they're much smaller scale, but would we be able to see that, or just the difference between smaller and
That's an interesting question. Maybe. I don't know the actual answer. Sorry about that. But that's a good question. Yeah. Yeah.
Question on the animation that you put up.
Okay.
The number of particles in the animation, did they just simulation? Did they put in particles that were dark matter that did not interact, and then also particles that did interact to get the structure?
Yep.
And if so, what was the the overlay? I think you showed the structure of the observer's matter. What did the dark matter look like? Did it filter out all the interactions? Did you just overlay? What's the structure of dark matter?
So the dark matter is actually along the whole. So the purple is dark matter as well. So it's like the very bright spots are where the galaxies are, and the filaments are mostly dark matter. Yep.
So when the Large Hadron Collider was being proposed, didn't the supersymmetry guys hold out high hopes that it was going to show some evidence of these ultramassive particles
Man.
that were built into their theory? Have they seen anything?
These are great questions, by the way. So one of the best candidates for a WIMP was something called the lowest energy or the lowest mass supersymmetric partner. But since supersymmetry is supersymmetry is not in question, but the simplest kind of supersymmetry is now in question because of what you said at the Large Hadron Collider. So that's no longer a candidate for our dark matter kind of. But that doesn't mean there can't be dark matter. It just means that it may not come from supersymmetry.
What a great presentation tonight.